the seafloor is silent. Not the peaceful silence of a sleeping ocean, but the terrible quiet of a graveyard. Shells dissolve into nothing. Coral skeletons crumble like ash. In water that should teem with life, nothing moves except the slow drift of death. 252 million years ago, something turned Earth's oceans into a planetary killing machine. This is the story of how almost everything in the sea died, not from a meteor strike or a sudden cataclysm, but from something far more insidious. The oceans themselves became toxic, acidic, suffocating, and for 10 million years afterward, they stayed that way. What happened at the end of the Permian period represents the closest Earth has ever come to losing complex life entirely. Understanding how this ancient catastrophe unfolded isn't just an academic exercise in paleontology. It's a window into how planetary systems can tip past a point of no return. The numbers alone should make you pause. 81% of all marine species vanished. Not just individuals, but entire species, erased from existence. 70% of land vertebrates gone, 96% of marine invertebrates extinct. When scientists talk about the Big Five mass extinctions, they save special reverence for this one. The Great Dying, they call it, and the name doesn't exaggerate. Before this event, Earth's oceans hosted reef systems that had flourished for hundreds of millions of years. After it, those reefs simply disappeared for 10 million years. An entire architectural form of life, gone. Walk along any coastline today and you'll see shells washing up on the beach. Pick one up, feel its weight, trace the ridges of its spiral. That shell exists because ocean chemistry allows it to exist. The water contains enough dissolved carbonate, the right pH balance, the correct mineral saturation. These conditions have persisted throughout human history, throughout all of recorded civilization, back through the ice ages and beyond. We take them for granted, these invisible chemical balances that make shelled life possible, but they haven't always been there, and they won't always be there. The Permian extinction proves that beyond any doubt. The event we're examining happened over thousands of years, maybe tens of thousands in its most intense phases. That sounds like a long time until you realize the aftermath lasted millions of years. Millions of years during which the oceans remained fundamentally broken, hostile to complex life, dominated by bacteria and algae rather than animals. The extinction boundary itself, the specific layer of rock where you see the fossils disappear, is often just centimeters thick. In that thin band of ancient stone compressed by time and burial lies the record of ecological collapse on a global scale. Scientists can read this record with extraordinary precision now. They can measure the chemistry of the water from isotopes trapped in fossil shells. They can determine oxygen, levels from the minerals in seafloor muds. They can track temperature from the ratio of different oxygen atoms bonded in ancient carbonates. They can even estimate how fast carbon was released into the atmosphere by modelling the carbon isotope shifts seen globally. Every measurement points to the same conclusion. The end Permian Ocean didn't just become hostile, it became actively lethal, a chemical weapon of planetary proportions. To understand the scale of what was lost, you need to picture the Permian Oceans as they existed before the catastrophe. These weren't the oceans we know today. The supercontinent Pangaea dominated the globe, a massive C-shaped landmass that stretched from pole to pole. Most of Earth's land was locked into this single continent, surrounded by the vast Panthalassic Ocean to the west and the smaller Tethys Sea nestled in the sea's curve to the east. The geography alone created unique conditions. Pangaea's interior was harsh desert, baking under relentless sun, but its coastlines hosted thriving marine ecosystems unlike anything in the modern world. Along the shallow continental margins, reef systems stretched for thousands of kilometers. But these weren't coral reefs in the modern sense. Corals existed, certainly. The rugose corals, sometimes called horn corals for their conical shape, had been building reefs since the Ordovician period, hundreds of millions of years earlier. Alongside them lived the tabulate corals, colonial forms that constructed horizontal platforms of calcite. But in the Permian, they shared their architectural role with a stunning diversity of other organisms. Sponges, not the soft bath sponges you might imagine, but massive calcareous structures, contributed to reef frameworks. Some grew into shapes resembling vases or goblets, others formed encrusting sheets. Brachiopods covered the seafloor in vast meadows. These shelled creatures, superficially resembling clams but entirely unrelated, filtered nutrients from the water column. The productive brachiopods, one of the most successful groups, had developed an unusual lifestyle. Rather than attaching to rocks by a fleshy stalk like most brachiopods, they simply lay on the sediment, one valve embedded in the mud, the other valve facing up, filtering food from the water. Some species developed elaborate spines, creating a platform that kept them elevated above the seafloor. Others grew to impressive sizes, with shells spanning 20 centimeters or more. The spiriferids represented another major brachiopod group. Their shells were widest at the hinge line, giving them a distinctive butterfly wing appearance when viewed from above. Inside each shell, intricate spiral structures supported the lophophore, the feeding organ unique to brachiopods. These spirals were so complex that their fossilized forms, sometimes preserved in exquisite detail, looked like miniature sculptures. Hundreds of brachiopod species existed, from tiny button-sized forms nestled in crevices to hand-span specimens dominating the open seafloor. Alongside brachiopods lived bryozoans, colonial animals that built delicate branching structures. Each colony consisted of thousands or millions of individual zooids, tiny creatures each living in its own chamber. The chambers connected through pores, allowing the colony to function as an integrated organism. Bryozoan colonies could take many forms. Some grew as lacy fans, each frond made up of parallel rows of zooids. Others formed thick encrusting masses. Still others created twiggy bushes reminiscent of heather. The diversity of form matched the diversity of species, with hundreds of different types occupying various ecological niches. Crinoids, the sea lilies, swayed on their stalks in the currents. These echinoderms, relatives of modern starfish and sea urchins, had a body plan that seems almost alien to us today. A flexible stalk, made of stacked calcite discs, anchored them to the sea floor. At the stalk's top sat the body proper, called the calyx, protected by interlocking plates of calcite. From the calyx extended feathery arms, often branching multiple times, creating a crown that could span 30 centimeters or more. The arms were covered with tiny tube feet that passed captured food particles down to the mouth at the center. Some seafloor communities were virtual forests of these creatures, the stalks packed so densely that fragments of their skeletons dominate certain rock layers. In the open water above, ammonoids spiraled through the depths. These cephalopods, relatives of modern nautilus, squid and octopus, had shells coiled like ram's horns. The shells were divided into chambers by walls called septa. The animal lived in the outermost chamber, extending its tentacles to capture prey. The inner chambers were filled with gas, providing buoyancy. By adjusting the gas pressure, ammonoids could control their depth. They range from species with shells as small as coins to giants with coils measuring more than a meter in diameter. The largest were among the most formidable predators in Permian seas. Competing with ammonoids for dominance of the water column were early sharks and bony fish. The sharks of the Permian were diverse, though none quite resembled the white sharks and hammerheads familiar today. Many belonged to extinct groups like the cladodonts and hybodonts. The bony fish included both ray-finned forms, ancestors of most modern fish, and lobe-finned varieties. Some had developed crushing teeth to feed on shelled invertebrates. Others had sharp teeth for catching smaller fish. The marine food webs of the Permian were complex, multi-layered hierarchies with numerous predators, prey, filter feeders, scavengers, and decomposers. On the seafloor, trilobites still scuttled through the sediment, though they were already in decline by the late Permian. These iconic arthropods, with their distinctive three-lobed bodies and compound eyes, had been incredibly diverse, earlier in the Paleozoic. By Permian times, they had been reduced to perhaps a dozen genera worldwide, clinging to existence in specialized niches. Most were small, none exceeded a few centimeters in length. They fed on detritus and small organisms in the sediment, playing a role similar to modern crustaceans. The final trilobite species lived in deeper water, below the zones where most other marine life concentrated. They would be among the extinction's casualties. These creatures shared something crucial, something that would doom most of them. They built their bodies from calcium carbonate, shells, skeletons, protective armor, all constructed from minerals dissolved in seawater. For brachiopods, the shell was made of calcite, the more stable form of calcium carbonate. For many mollusks, the shell was aragonite, slightly less stable. Corals used aragonite for their skeletons. Crinoids used calcite plates. Regardless of the specific mineral, the process was the same. The organism extracted calcium ions and carbonate ions from the water and bonded them together into solid crystal structures. This strategy had worked flawlessly for hundreds of millions of years. The chemistry of the ocean had remained stable enough to support it. Seawater was supersaturated with respect to both calcite and aragonite, meaning it contained more dissolved calcium and carbonate than pure water could hold. The excess drove precipitation, making shell formation energetically favourable. Organisms still had to work to build their shells, to control the crystallization process, to shape the minerals into functional structures. But the basic chemistry was on their side. That stability was about to be shattered by an event of such geological violence that its scars still mark the Earth today. In what is now Siberia, stretching across an area larger than Western Europe, the Earth's crust began to split. Not slowly, not gradually, but in a volcanic convulsion that would pump more lava onto the surface than any eruption in the last half-billion years. The Siberian Traps, as geologists call them today, represent one of the largest igneous provinces ever documented. The name Traps comes from the Swedish word for stairs, trappa, referring to the step-like appearance of the eroded lava flows, but don't let the mundane name fool you. This was apocalyptic volcanism on a scale that defies easy comprehension. Imagine not a single volcano, but an entire region of the planet breaking open, fissures hundreds of kilometers long pouring out molten rock. The lava didn't erupt in explosive Vesuvius-style blasts. It simply welled up from the ground in enormous volumes, spreading across the landscape in floods of molten basalt. Individual flows could cover thousands of square kilometers, pooling hundreds of meters deep in low-lying areas. Flow after flow accumulated, building a plateau of solidified lava that eventually covered roughly 7 million square kilometers, an area about the size of Australia. The numbers become almost meaningless at this scale. The Siberian Traps erupted approximately 1.4 million cubic miles of lava. That's 6 million cubic kilometers. To visualize that, imagine burying the entire United States under a layer of basalt 400 meters thick, or picture a cube of solid rock 180 kilometers on a side. The mass involved staggers the imagination, but volume alone doesn't capture the true horror. It's the speed that matters, the rate at which all that molten rock reached the surface. This wasn't a slow seepage of lava over millions of years, the kind of gentle volcanism that builds Hawaiian shield volcanoes. The main pulse of Siberian Traps activity occurred in less than 1 million years, possibly as little as 200,000 years. Some estimates suggest the most intense phase lasted just 60,000 years. In geological terms, that's instantaneous. It's a snap of the fingers, a blink of an eye. The Earth was hemorrhaging molten rock at an unprecedented rate. Dating these ancient eruptions requires sophisticated techniques. Scientists use uranium-lead dating of zircon crystals, tiny mineral grains that form when magma crystallizes. Zircon incorporates uranium atoms into its crystal structure, but excludes lead. The uranium then decays radioactively, slowly transforming into lead over millions of years. By measuring the ratio of uranium to lead in a zircon crystal, and knowing the decay rate, scientists can calculate when the crystal formed. The technique is precise enough to resolve ages within a few 100,000 years, even for rocks 250 million years old. Uranium-lead dating of zircons from the Siberian Traps has pinned down the timeline with remarkable precision. The eruptions began at 252.8 million years ago, give or take 500,000 years. The peak period of magma emplacement, when the most lava reached the surface, occurred between 252.3 and 251.9 million years ago. That's the critical window. And here's the stunning part. The Permian-Triassic boundary, defined by the disappearance of specific fossil species and the appearance of new ones, has been dated using the same techniques to 251.9 million years ago, with a precision of less than 40,000 years. The overlap is exact. The peak of Siberian Traps volcanism coincided precisely with the extinction horizon visible in rock layers across the globe. The match isn't approximate, it's within the margin of error of the dating techniques. When scientists achieved this level of chronological resolution, published in 2014, it eliminated any remaining doubt. The Siberian traps triggered the extinction. The volcano didn't just happen to erupt around the same time life was dying, it was the cause, the smoking gun. But how? Lava itself, destructive as it is, affects only the immediate surroundings of an eruption. A lava flow can bury forests, vaporize lakes, obliterate everything in its path, but its influence is strictly local. You can find plants growing right up to the edges of century-old lava flows in Hawaii. The Siberian traps are located in a remote part of northern Asia, thousands of kilometers from the shallow tropical seas where most Permian marine life thrived. The lava never reached the oceans. So how did volcanism in Siberia kill marine life in China, in Greenland, in what is now the United States? The answer lies not in the rock itself, but in what came with it. Volcanoes don't just erupt lava, they release gases, stupendous quantities of gases. Molten rock, or magma as it's called while underground, contains dissolved volatiles. Water vapor, carbon dioxide, sulfur dioxide, hydrogen chloride, hydrogen fluoride. These gases are held in solution by pressure, like carbon dioxide in a sealed bottle of soda. When magma rises toward the surface, pressure decreases. The gases exsolve, forming bubbles. In explosive eruptions, the bubbles grow so violently they shatter the magma into fragments, creating ash clouds and pyroclastic flows. In flood basalt eruptions like the Siberian traps, the gases escape more gradually, but in absolutely enormous quantities. The Tunguska Basin, where much of the Siberian traps magma forced its way to the surface, wasn't empty rock. It contained thick layers of sedimentary rocks deposited over hundreds of millions of years. Limestone, dolomite, gypsum, and hydrite, the carbonate and evaporate minerals that form in shallow seas. Coal beds, accumulated from ancient swamps. Organic rich shales, black mudstones packed with the remains of microscopic marine life. These rocks held vast quantities of carbon and sulfur, locked away in solid form, chemically stable, harmlessly buried. When superheated magma, at temperatures exceeding 1000 degrees Celsius, intruded into these rocks, it didn't just melt them, it baked them, it cooked them, it thermally decomposed them. Coal beds combusted, burning at temperatures hot enough to melt the surrounding rock into slag. Limestone decomposed according to simple chemistry, calcium carbonate breaking down into calcium oxide and carbon dioxide. Organic material in shales volatilized, its carbon released as CO2 and methane. Gypsum broke down, releasing sulfur dioxide. The sedimentary rocks of the Tunguska Basin became a carbon and sulfur bomb, and the Siberian trap's magmatism lit the fuse. The result was a pulse of gas emission unprecedented in recent Earth history. Recent estimates, based on carbon isotope modelling and geochemical proxies, suggest the Siberian traps released approximately 36,000 gigatons of carbon into the atmosphere. Let that number sink in. 36,000 gigatons. A gigaton is 1 billion metric tons, or 1 trillion kilograms. We're talking about 36 trillion metric tons of carbon. To put that in perspective, that's roughly 4,000 times more than humanity has released through all fossil fuel burning since the Industrial Revolution began. It's more carbon than is currently stored in all the world's forests combined. It's a geological catastrophe made tangible, but the total amount, staggering as it is, only tells part of the story. The rate of emission matters just as much, perhaps more. Carbon dioxide naturally cycles through Earth's climate system. Volcanoes emit it. Weathering of rocks consumes it. Photosynthesis removes it from the air. Respiration and decay return it. On geological timescales, these processes balance, keeping atmospheric CO2 relatively stable. But the Siberian traps weren't emitting carbon at geological background rates. They were flooding the atmosphere faster than the natural carbon cycle could handle. Models combining carbon isotope data with our understanding of carbon cycle dynamics indicate the main pulse of carbon emission occurred at a rate of about 4 to 5 gigatons per year. Some phases may have been even faster, perhaps 10 gigatons per year. That might not sound like much. Humanity currently emits around 11 gigatons of carbon per year from fossil fuels. But here's the crucial difference. Human emissions have been ramping up for only about 200 years, accelerating most rapidly in just the last few decades. The Siberian traps maintained their emission rate for tens of thousands of years without pause. The ocean and atmosphere couldn't absorb carbon that quickly, without profound changes. Think of it like filling a bathtub. If you turn the tap on slowly, water fills the tub gradually, and the drain can keep up maintaining a steady level. but if you turn the tap on full blast, the water rises faster than the drain can handle, and the tub overflows. The Siberian traps turned the carbon tap on full blast. The Earth system's natural carbon sinks. The processes that normally absorb and sequester CO2 couldn't keep pace. Carbon dioxide accumulated in the atmosphere and consequently in the ocean. This massive injection of carbon dioxide fundamentally altered Earth's atmosphere and oceans. Carbon dioxide isn't just a greenhouse gas that warms the planet, though it certainly does that. When it dissolves in seawater, it changes the ocean's chemistry in profound ways that strike at the very foundation of marine life. The process is straightforward, but its consequences are devastating. Carbon dioxide reacts with water to form carbonic acid. The reaction is rapid and spontaneous. H2O plus CO2 yields H2CO3. Carbonic acid then dissociates, splitting into hydrogen ions and bicarbonate ions. Those hydrogen ions are what makes water acidic. Acidity is just a measure of hydrogen ion concentration. More hydrogen ions means lower pH means more acidic, but there's a second effect, equally important and even more insidious. The hydrogen ions also react with carbonate ions, the building blocks that marine organisms use to construct their shells and skeletons. The carbonate ions combine with hydrogen to form bicarbonate, effectively removing them from solution. So dissolving carbon dioxide in seawater does two things simultaneously. It increases acidity and it decreases carbonate availability. Both changes make it harder for organisms to build calcium carbonate structures. This is ocean acidification, and the rock record from the Permian-Triassic boundary preserves direct evidence of it. Scientists have found multiple independent lines of evidence, each telling the same story. By analysing boron isotopes in fossil shells, they can reconstruct ancient seawater pH. Boron in seawater exists in two chemical forms, boric acid and borate ion. The ratio between these two forms changes systematically with pH. When organisms incorporate boron into their shells, they record this ratio, creating a chemical memory of the ocean's acidity at the time the shell formed. Detailed studies of brachiopod shells from sites in southern China and northern Greenland reveal a shocking shift. Surface ocean pH dropped from approximately 8.2, slightly higher than modern levels, to about 7.5. That's a drop of 0.6 to 0.7 pH units over approximately 10,000 years. The shift appears in multiple sections from different locations worldwide, confirming it was a global phenomenon, not some local aberration. That number might seem small to someone unfamiliar with the pH scale. After all, it's less than 1 unit on a scale that runs from 0 to 14, but pH is a logarithmic scale, not a linear one. Each whole number represents a tenfold change in hydrogen ion concentration. A drop of 0.7 units represents an increase in hydrogen ions by a factor of roughly 5. The ocean became 5 times more acidic. For comparison, modern oceans have acidified by about 0.1 units since the Industrial Revolution, from pH 8.2 to 8.1. Marine biologists already consider this change alarming, potentially catastrophic for coral reefs and other calcifying organisms. The Permian acidification was 7 times more severe, and unlike today's relatively gradual change, the Permian shift happened fast enough that evolution couldn't keep pace. Calcium isotopes tell a complementary story. When seawater is saturated with carbonate, organisms can easily extract calcium to build their shells. But when the water becomes undersaturated, when there isn't enough carbonate available, organisms have to work harder. They discriminate differently between calcium isotopes during shell formation. This changes the calcium isotope ratio in their shells. Studies of calcium isotopes across the Permian-Triassic boundary show a pronounced negative excursion, exactly the signature expected from ocean acidification and carbonate undersaturation. The organisms most vulnerable were exactly those that dominated Permian seas: brachiopods with their heavy calcite shells, corals constructing their skeletons from aragonite, bryozoans, crinoids, calcareous sponges, all the reef builders and hard-bottom dwellers. They required stable carbonate saturation in the water to build their structures. Their physiology was optimized for an ocean where shell building was energetically cheap. Many didn't even have sophisticated mechanisms for regulating their internal chemistry. They simply took calcium and carbonate from the surrounding water and precipitated it into shell material. As the ocean acidified, that strategy failed catastrophically. Shell growth slowed, then stopped. Shells grew thin and brittle. Existing structures began to dissolve, literally eaten away by the chemistry of the water itself. Larvae couldn't calcify properly. Juvenile survival rates plummeted. Species that had thrived for millions of years found themselves unable to reproduce successfully. The acidification didn't kill adult organisms instantly. It killed them by taking away their ability to maintain their bodies, to produce offspring, to continue as species. The evidence is written directly in the rock. In many Permian-Triassic boundary sections, you can see the change with your own eyes if you know what to look for. Below the boundary, limestone layers are packed with fossils, shell fragments, coral remains, crinoid stems, brachiopod valves, the accumulated detritus of thriving ecosystems. The limestone itself is often biohermal, meaning it formed as a reef or reef rubble. The rock is literally made of the organisms that built it. Above the boundary, the fossils vanish. The rock changes character, becoming fine-grained mudstone or siltstone, dark and barren. In some places, thin limestone layers persist, but they're not bioherms. They're chemical precipitates or microbialites, formed by bacteria rather than animals. The shells that do remain, the last survivors clinging to existence in the extinction's early stages, show obvious signs of stress. Their surfaces are etched and pitted, corroded by acidic water. Their fine ornamentation is dissolved away. Their crystal structure is disrupted. These are the shells of organisms dying slowly, their protective armor disintegrating even as they lived inside it. But acidification alone cannot explain the totality of what happened. Many organisms that weren't heavily calcified also died. Fish, which don't build calcium carbonate structures. Sharks with their cartilaginous skeletons. Soft-bodied invertebrates like many worms and jellyfish. Ammonoids, though they had shells, were mobile and relatively adaptable. Yet they suffered severe extinction rates. Something else was killing life in the oceans. Something that affected even creatures that could tolerate acidic conditions. That something was oxygen, or rather, its absence. Ocean anoxia, the depletion of dissolved oxygen in seawater, left its own distinct signature in the rock record. When bottom waters lose their oxygen, the chemistry of the sediment changes in predictable ways. Iron, normally locked up in rust-coloured oxides under oxygenated conditions, gets reduced to more mobile forms. It can dissolve and migrate through sediment. When it encounters sulfur, which is also behaving differently under anoxic conditions, they combine to form pyrite, iron sulfide, fool's gold. The small cubic crystals of pyrite are diagnostic of oxygen-depleted environments. But scientists can go further than just noting pyrite's presence. They can analyse the forms it takes. Under oxygen-depleted but not completely anoxic conditions, pyrite forms as framboids, tiny spherical clusters of even tinier crystals, resembling raspberries under a microscope. The size distribution of these framboids is diagnostic of oxygen levels. Small framboids, less than 5 micrometers in diameter, form only under severely oxygen-depleted or completely anoxic conditions. Larger framboids can form in less extreme environments. By measuring thousands of framboids from rock samples and analysing their size distribution, scientists can reconstruct ocean oxygen levels with surprising precision. Studies of pyrite framboids from Permian-Triassic boundary sections worldwide show a consistent pattern. Below the boundary, framboid sizes are relatively large and variable, indicating oxygenated or only mildly oxygen-depleted conditions. At and above the boundary, framboids become dramatically smaller and more uniform, diagnostic of euxinic conditions. The shift happens rapidly, often within a single metre of rock section, corresponding to perhaps 10,000 years of deposition. Iron speciation provides another independent line of evidence. Scientists can chemically extract different forms of iron from rock samples. Highly reactive iron, the forms that are mobile under anoxic conditions, versus unreactive iron, the forms locked in silicate minerals. The ratio between these two types changes systematically with bottom water oxygen levels. When bottom waters are oxygenated, most iron in sediments is unreactive. When bottom waters become anoxic, reactive iron accumulates. Studies of iron speciation across the Permian-Triassic boundary show an abrupt shift to anoxic conditions at the extinction horizon. Uranium isotopes provide yet another window into ocean redox conditions, not just at the seafloor but globally. Uranium in seawater has two isotopes. Uranium-238 and uranium-235 present in a specific ratio. Under oxygenated conditions, uranium stays dissolved in seawater. But when oxygen disappears from bottom waters, uranium precipitates out and gets buried in seafloor sediments. This changes the isotope ratio of uranium remaining in seawater, because the two isotopes precipitate at slightly different rates. Carbonate rocks that form from seawater record this isotope ratio. By analysing uranium isotopes and carbonates, scientists can estimate what fraction of the global ocean floor was anoxic at any given time. Studies of uranium isotopes from the Permian-Triassic boundary section at Darwin in southern China reveal a dramatic shift. The isotope ratio changes from values indicating relatively small areas of anoxic seafloor to values indicating a six-fold expansion of anoxic conditions. Enormous regions of the ocean floor, possibly covering millions of square kilometres, lost their oxygen entirely. This wasn't a local phenomenon affecting one marginal sea, it was a global ocean catastrophe. The mechanism behind this widespread anoxia is straightforward, but the scale is staggering. Oxygen dissolves in water according to Henry's law, which states that the amount of gas that dissolves is proportional to its partial pressure in the atmosphere and inversely proportional to temperature. Warmer water holds less dissolved gas than cold water. This is why soda goes flat faster when it's warm. As the Siberian traps pumped greenhouse gases into the atmosphere, global temperatures soared. Estimates based on oxygen isotopes in fossil shells, combined with temperature proxies from paleosol carbonates on land, suggest sea surface temperatures in tropical regions reach 35 degrees Celsius, possibly as high as 40 degrees. That's 95 to 104 degrees Fahrenheit. Bathwater warm, hot tub hot. At those temperatures, surface waters could hold perhaps 30% less oxygen than modern tropical seas. That alone would stress marine ecosystems severely. Most marine organisms are ectothermic, meaning their body temperature matches the surrounding water. Their metabolic rates increase with temperature, and their oxygen demand increases proportionally. So just when organisms needed more oxygen to support their metabolism, the ocean held less. But the warming triggered a cascade of additional effects that turned stress into catastrophe. Warmer water is less dense than cold water. This is basic physics, a consequence of thermal expansion. In modern oceans, this density difference drives circulation. Cold, dense water at the poles sinks and flows along the ocean floor toward the equator, carrying oxygen to the depths. Warm, less dense water in the tropics flows toward the poles at the surface, where it cools, sinks, and begins the cycle again. This thermohaline circulation, driven by temperature and salinity differences, constantly refreshes the ocean, delivering oxygen even to the deepest trenches. It's why fish can live in the deep sea despite being thousands of meters from the atmosphere. But in the end, Permian, warming destroyed this circulation. When tropical surface waters heated to extreme temperatures, they became so much less dense than deeper waters that they stopped mixing. A strong density gradient developed, creating a stratified ocean with warm, low-density water sitting atop cooler, denser water. The boundary between these layers, the thermocline, became a barrier to vertical mixing. Oxygen in surface waters couldn't reach the depths. Deep water, cut off from the atmosphere, slowly consumed its oxygen through respiration and decay, and no fresh oxygen arrived to replace it. Computer models of end-Permian ocean circulation, using the geography of Pangaea and estimated temperature distributions, confirm this scenario. The models show thermohaline circulation weakening dramatically, possibly stopping altogether in some ocean basins. The residence time of deep water, the average time before it gets replaced by surface water, increased from hundreds of years in the modern ocean to thousands of years in the end-Permian. That's a staggering slowdown. Deep ocean waters became essentially stagnant, cut off from the life-giving oxygen of the atmosphere. Without circulation, the deep ocean became anoxic through simple consumption. Organic matter, dead plankton, fecal pellets, the constant rain of biological detritus from surface waters sank to the seafloor. Bacteria consumed this organic matter, using oxygen as an electron acceptor in respiration. In a healthy ocean, circulation replenishes this oxygen faster than bacteria can consume it. But in the stagnant end Permian Ocean, consumption outpaced replenishment. Oxygen levels dropped steadily, first to hypoxic levels, less than 2 milligrams per litre, stressful for most organisms, then to anoxic levels, essentially zero oxygen. And in many places the chemistry got even worse. The situation was exacerbated by changes on land. As temperatures rose and climate patterns shifted, vegetation on Pangaea's interior collapsed. The fossil record shows a dramatic die-off of plants in many regions, what paleobotanists call the coal gap, because coal deposits, which form from accumulated plant matter, disappear from the rock record for millions of years. Without plants anchoring soil and absorbing runoff, erosion intensified dramatically. Rivers carried unprecedented loads of sediment and nutrients into coastal waters. These nutrients, particularly nitrogen and phosphorus, acted as fertilizer. Algal blooms exploded across coastal seas. The blooms were intense but short-lived. When the algae died, their bodies sank en masse, providing a sudden flush of organic matter to bacteria on the seafloor. Oxygen consumption spiked. Coastal waters, normally the most productive and oxygen-rich parts of the ocean, turned hypoxic, then anoxic. The oxygen minimum zones, normally restricted to intermediate depths in the open ocean, expanded both horizontally onto continental shelves and vertically toward the surface. Dead zones developed, regions where oxygen dropped so low that mobile organisms couldn't survive. These zones weren't static. They expanded and contracted with seasons, with algal bloom cycles, with shifts in circulation. But their overall extent grew relentlessly as the warming continued, as more carbon dioxide entered the system, as vegetation on land continued to collapse. By the time of the main extinction pulse, oxygen minimum zones covered vast areas. Studies combining multiple redox proxies suggest that perhaps 30 to 40% of the global ocean floor was anoxic at the extinction maximum. The impact on marine life was devastating. Sessile organisms, those attached to the seafloor, had nowhere to flee. Bottom-dwelling fish, crustaceans, mollusks, echinoderms, all required oxygen-rich water. When the water turned hypoxic, they died. When entire regions became dead zones, ecosystems collapsed. Species that had evolved for hundreds of millions of years in oxygenated oceans had no adaptations for anoxia. Their physiologies were optimized for an ocean that had stopped existing. Mobile organisms fared somewhat better. Fish could swim to shallower water, to regions where circulation still delivered oxygen. Ammonoids could adjust their buoyancy, moving up or down to find oxygenated layers, but even this provided only temporary refuge. Because the chemistry was getting worse, anoxia was just the beginning. Under those oxygen-starved conditions, an even more sinister process took over, transforming dead zones into actively toxic killing zones. When bacteria decompose organic matter in the presence of oxygen, they produce carbon dioxide and water, relatively benign products. But when oxygen isn't available, bacteria turn to other molecules as electron acceptors. One of the most thermodynamically favourable alternatives is sulfate. Sulfate is abundant in seawater, roughly 2,800 milligrams per litre. Sulfate-reducing bacteria thrive in anoxic sediments, and they produce hydrogen sulfide as a waste product. In small amounts, this isn't a problem. The hydrogen sulfide remains buried in the sediment or gets reoxidized when it encounters oxygen in the water above. But when anoxia becomes widespread and intense, when organic matter flux overwhelms the system, hydrogen sulfide can escape into the water column itself. This is euxemia, the presence of free hydrogen sulfide in the water, and it transforms anoxic dead zones into actively toxic environments. Hydrogen sulfide is viciously poisonous to most complex life, as anyone who has encountered sewer gas or worked around oil wells knows. It smells like rotten eggs, that distinctive sulphurous stench warning of danger. But the danger isn't just the smell. Hydrogen sulfide interferes with cellular respiration, binding to cytochrome C oxidase, the enzyme that cells use to process oxygen. It competes with oxygen for the same binding sites. Even at concentrations of just a few parts per million, it can inhibit respiration. At higher concentrations, it's rapidly lethal. The bacteria that produce hydrogen sulfide don't just tolerate it, they thrive in its presence. They're anaerobic, they don't need oxygen. Some species, the green sulfur bacteria, can even photosynthesize using hydrogen sulfide instead of water. They're coloured, purple or green by unique pigments, and they can bloom in massive numbers when sulfide becomes available in the photic zone. Normally they're restricted to extreme environments, places like the Black Sea where a permanent anoxic layer lies below 100 meters depth. But in the end Permian Ocean, these bacteria spread across large areas. Biomarkers preserved in Permian-Triassic boundary rocks confirm this. Biomarkers are organic molecules that resist degradation and can survive for hundreds of millions of years in rocks. Different organisms produce characteristic biomarkers. Green sulfur bacteria produce a specific class of molecules called aryl isoprenoids. These compounds are found nowhere else in nature. When they appear in ancient rocks, they're diagnostic evidence that green sulfur bacteria were present, and they appear exactly at the Permian-Triassic boundary in sections worldwide. Not just present, but abundant, dominant, indicating that these bacteria had taken over large swathes of the ocean. The appearance of green sulfur bacteria biomarkers is particularly significant because these organisms require both light and hydrogen sulfide. They live only where the two overlap in the photic zone under euxinic conditions. In a healthy ocean, this never happens. Hydrogen sulfide is confined to sediments or to deep waters far below where light penetrates. The presence of these biomarkers therefore proves that euxenia reached the sunlit surface layers of the ocean. Hydrogen sulfide rose from the depths into the photic zone. The extent of euxenia varied geographically and through time. Some regions, particularly restricted basins and shallow continental shelves with limited circulation, developed euxinic conditions that reached right to the surface. The water would have appeared purple or green from massive blooms of sulfur bacteria. The stench would have been overwhelming. Nothing that required oxygen could survive. Other areas, especially the open ocean, likely maintained oxygenated surface waters even as the depths turned sulfidic. But everywhere, the habitable zone shrank dramatically. Modern computer models of Permian ocean chemistry, calibrated against the geochemical proxies, paint a disturbing picture. The ocean developed a three-layered structure. At the surface, a thin layer of oxygenated but extremely hot water, tolerably only to organisms adapted to high temperatures. At intermediate depths, oxygen minimum zones that were anoxic, or at best hypoxic, but not yet sulfidic. At depth, fully euxinic conditions, with free hydrogen sulfide rising upward toward the chemocline. The chemocline, the boundary between oxygenated and sulfidic water, was dynamic. It moved up and down through the water column as conditions fluctuated. During periods of intense warming, or after large algal blooms when organic matter flux spiked, the chemocline could shoal dramatically. Models suggest it sometimes reached to within a few meters of the surface on continental shelves. During these episodes, hydrogen sulfide would have escaped directly into the atmosphere. There's evidence this actually happened. Some Permian plant fossils from boundary sections show damage consistent with exposure to sulfur dioxide. Sulfur dioxide forms when hydrogen sulfide in air oxidizes. It's also toxic, and it causes characteristic damage to plant tissues. The damage appears as malformations of pollen grains and spores, abnormal shapes and sizes that indicate the plants were stressed during reproduction. The pattern appears globally, suggesting widespread atmospheric sulfur pollution. If hydrogen sulfide reached the atmosphere in large quantities, it would have additional consequences beyond direct toxicity. Hydrogen sulfide and sulfur dioxide both react with ozone, the form of oxygen that makes up the stratospheric ozone layer. This layer protects life from harmful ultraviolet radiation from the sun. Destroy the ozone layer and UV flux increases, damaging DNA, inhibiting photosynthesis, causing mutations. Some researchers have proposed that ozone destruction contributed to the end Permian extinction, particularly on land. The evidence is circumstantial, but the mechanism is plausible. The oceans weren't just suffocating and acidifying, they were actively toxic, producing poisons that killed marine life directly and possibly damaged terrestrial ecosystems as well. The combination of stressors, each amplifying the effects of the others, created a cascade of death that few organisms could escape. And critically, these weren't brief pulses of bad conditions. The geochemical record shows that anoxia and euxenia persisted not for thousands of years, but for millions of years into the early Triassic. The ocean remained broken long after the main killing had finished. The extinction didn't happen all at once. High-resolution studies of boundary sections, particularly in South China where sedimentation rates were rapid, and the fossil record is exquisite, reveal a more complex pattern. There were two distinct pulses of extinction, separated by perhaps 60,000 years. This two-phase structure is visible in multiple sections worldwide and appears to be a real feature of the event, not an artifact of incomplete preservation. The first extinction pulse occurred in the latest Permian, approximately 60,000 years before the formal Permian-Triassic boundary, as defined by the appearance of the Conodont Hindeadus parvus. This pulse eliminated many species but was selective in curious ways. Surface-dwelling organisms, particularly those adapted to warm tropical conditions, suffered disproportionate losses. The rugose and tabulate corals that had built reefs for hundreds of millions of years vanished almost entirely. Radiolarians, single-celled organisms that construct intricate silica skeletons and float in the surface waters, underwent a catastrophic decline. Large foraminifera, another group of shell-bearing protists that lived in shallow tropical waters, disappeared from many regions, but deeper water organisms fared relatively better during this first pulse. Many brachiopod species that lived on the continental slope below the thermocline survived. Some ammonoid groups persisted, though with reduced diversity. Certain bivalves even expanded their range, moving into ecological niches vacated by extinct competitors. The pattern suggests that the first pulse was driven primarily by extreme heat in surface waters. Organisms adapted to cooler conditions could retreat to depth and survive. Those that required warm surface waters, like reef-building corals, had nowhere to go when temperatures exceeded their thermal tolerance. The first pulse also saw shifts in biogeography, species distributions across the globe. Some tropical species undertook long-distance migrations toward higher latitudes, moving poleward in search of cooler water. Fossil assemblages from what was then northern high-latitude regions, places like Spitsbergen and Greenland, show the sudden appearance of species that had previously been restricted to the tropics. These refugee populations survived the first pulse by fleeing to cooler waters, but their reprieve was temporary. Between the two pulses, there was a brief interval when conditions may have stabilized or even improved slightly. Some carbon isotope records show a minor recovery, a slight positive shift suggesting that carbon input had temporarily decreased. Some paleontological studies report a small increase in diversity, a few new species appearing, some surviving species expanding their range. But this recovery was incomplete and short-lived. The second pulse would prove even more devastating. The second extinction pulse occurred right at the Permian-Triassic boundary, as defined by Conodont biostratigraphy. It was even more severe than the first, sweeping away many survivors of the first pulse and restructuring marine ecosystems fundamentally. The timing correlates with a second major injection of carbon into the atmosphere, visible as another sharp negative shift in carbon isotope ratios. The carbon isotope record, measured from both carbonate rocks and organic matter, tracks the relative abundance of carbon-12 versus carbon-13 in the ancient ocean and atmosphere. Volcanic carbon and organic carbon are both enriched in the lighter isotope, carbon-12, compared to atmospheric carbon dioxide. When massive amounts of this light carbon are released, it shifts the isotopic ratio of the entire ocean-atmosphere system toward more negative values. The Permian-Triassic boundary shows one of the largest carbon isotope excursions in all of Earth history. The delta carbon-13 value, the standard measure used, shifts by 5 to 6 per mil. That's a huge change, representing the injection of thousands of gigatons of isotopically light carbon in a geologically brief interval. The second pulse appears to have been both faster and larger than the first. Carbon cycle models calibrated against the magnitude and rate of the isotope shift suggest emission rates spiked dramatically during this interval. Some estimates put the rate as high as 10 gigatons of carbon per year or more, double the rate of the first pulse. At these rates, the ocean's buffering capacity was completely overwhelmed. Carbonate alkalinity collapsed. Acidification intensified dramatically. The second pulse also saw the culmination of ocean anoxia and euxenia. All the redox indicators show maximum values at or just above the Permian-Triassic boundary. Pyrite framboids are smallest. Iron speciation ratios indicate widespread anoxic conditions. Uranium isotopes record maximum extent of global seafloor anoxia. Biomarkers for green sulfur bacteria reach peak abundance. The evidence converges on a single conclusion. Euxinic conditions expanded dramatically during the second pulse, spreading onto shallow continental shelves, shoaling to reach the photic zone over broad areas. the refuge zone of habitable mid-depth water, the narrow layer where organisms could escape both surface heat and deep water anoxia, collapsed. Organisms had nowhere left to hide. The combination of extreme heat, severe acidification, widespread anoxia, and toxic hydrogen sulfide created a perfect storm of mortality. Only organisms with extraordinary environmental tolerances, capable of handling all of these stresses simultaneously, had any chance of survival. The extinction selectivity patterns support this interpretation. Among benthic organisms, those living on or in the seafloor, extinction rates were catastrophic. Genera that had existed for tens of millions of years disappeared. Entire families went extinct. The brachiopods, which had been incredibly diverse with hundreds of species globally, crashed to fewer than 20 surviving species. Most belonged to just a handful of genera. The productids, the richtovenids, the litanids, the spiriferids, all the major groups that had dominated Paleozoic seafloors, gone. Bryozoans suffered similarly severe losses. Crinoids nearly went extinct entirely. Only a few species of mobile crinoids, not anchored to the seafloor, survived. The stalked crinoids, the classic sea lilies, were decimated. Calcareous sponges, which had been important reef builders, disappeared from most environments. The reefs themselves collapsed completely, not gradually, not over millions of years, but catastrophically. Below the boundary, you find reef facies, biogenic limestone formed by actively growing reef ecosystems. Above the boundary, no reefs, just mudstone and microbialite. The reefs disappeared from the geological record for 10 million years. This is the Triassic coral gap. Trilobites made their final exit. The last species, genera like Pseudophilipsia and Saginocrinites, clinging to existence in deep water refuges far from the killing fields of the shallow tropics, succumbed during the Second Pulse. After 300 million years of evolutionary success, one of the most iconic groups of Paleozoic arthropods vanished forever. They had survived earlier mass extinctions, adapted to ice ages and warm periods, dispersed across ancient seas. But they couldn't survive the end Permian catastrophe. Mollusks were hit hard, but not as severely as brachiopods. Many bivalve families went extinct, but others survived. Gastropods suffered significant losses, but retained more diversity than brachiopods. The difference likely relates to physiology and ecology. Many mollusks are more mobile than brachiopods. They can burrow into sediment, escaping bottom water anoxia. Some bivalves develop the ability to tolerate low oxygen conditions. Their physiology is generally more flexible, better able to regulate internal chemistry even when external conditions are hostile. Ammonoids underwent a massive bottleneck. Hundreds of Permian species went extinct. Only a handful of genera survived into the Triassic, but those that did survive subsequently radiated explosively, suggesting they retained genetic diversity and evolutionary potential. The ceratitids, one surviving group, would go on to dominate Triassic seas. But that recovery lay millions of years in the future. In the immediate aftermath of the extinction, ammonoid diversity was at its lowest point since the group first evolved. Fish suffered substantial but not total extinction. Many Permian families disappeared. The extinction rate at the species level may have exceeded 70 or 80%. But enough lineages survived to repopulate marine environments during the Triassic. The sharks, already declining through the Permian, reached extremely low diversity. Only a few lineages persisted. But again, these would eventually radiate to produce the diverse shark faunas of later periods. On land, the extinction was equally severe. The synapsids, mammal-like reptiles that had dominated terrestrial ecosystems since the Carboniferous, suffered catastrophic losses. Genera like Moschops, Dicynodon, and Lystrosaurus represent the few survivors. Lystrosaurus in particular became incredibly abundant after the extinction, a disaster taxon that flourished in the empty ecological landscape. But most Permian synapsid diversity was wiped out, 90% extinction at the genus level. The glossopterids, seed ferns that had formed vast forests across Gondwana, went extinct. The coal gap in the rock record, the absence of coal deposits for millions of years after the extinction, reflects the collapse of terrestrial vegetation. Without plants to hold soil, erosion intensified. Without organic matter accumulation, coal formation ceased. The terrestrial landscape became barren. dominated by ferns and lycopods, opportunistic plants that colonize disturbed ground. Complex forest ecosystems wouldn't return until well into the Triassic. In the immediate aftermath, both marine and terrestrial environments looked alien, broken. The fossil record from the earliest Triassic, the first few 100,000 years after the boundary, reveals ecosystems that were functioning only barely. Diversity remained extremely low. Community structure was simple, lacking the complex food webs and specialized niches that characterize healthy ecosystems. The organisms that did survive often showed signs of severe stress. The Lilliput effect, documented across many groups, saw surviving species dwarfing dramatically. Brachiopods that had been hand-sized before the extinction shrank to thumbnail dimensions. Gastropods that had shell diameters of several centimeters dwindled to just millimeters. Even some vertebrates became smaller. This dwarfing reflects chronic environmental stress, malnutrition, suboptimal growth conditions. The survivors were barely hanging on, growing slowly, reproducing inefficiently, maintaining only marginal populations. Some creatures actually expanded in the aftermath, but these were ecological weeds, generalist species that could tolerate harsh conditions. The bivalve Chloria appeared in enormous numbers, forming monospecific shell beds in many early Triassic sections. A single species, sometimes a single genus, covering the seafloor in vast numbers, excluding all competitors. This is the signature of disaster fauna, opportunistic species exploiting empty ecological space. But Claria didn't build complex ecosystems. It just occupied space, a biological placeholder marking the absence of diversity. Microbialites became widespread, far more common than they had been for hundreds of millions of years. These structures, formed by bacteria and algae, had dominated Precambrian oceans billions of years earlier. But with the evolution of grazing animals, they had largely disappeared from most environments. Now, with the grazers extinct or severely reduced, microbialites returned. They grew as thick mats covering hard surfaces, as isolated domes and columns, as reef-like structures rising meters above the seafloor. These are anachronistic facies, rock types that look like they belong in an earlier era of Earth history. Their return signals a fundamental disruption of ecosystem function. The biological pump, the process by which organic matter sinks from surface waters to depth, taking carbon with it, had largely ceased. Productivity was low, the ocean was biologically impoverished, barely sustaining life, and critically, conditions remained bad for a very long time. The geochemical proxies don't show rapid recovery. Temperature remained elevated through most of the early Triassic. Some studies document additional warming pulses, suggesting continued volcanic activity or positive feedbacks in the climate system. Ocean acidification persisted. Carbon isotope ratios remained negative. Anoxia and euxenia fluctuated but never fully disappeared. The system had been knocked into a dysfunctional state and couldn't easily recover. Why did recovery take so long? This remains one of the great puzzles of the end Permian extinction. Other mass extinctions, even severe ones like the Cretaceous Paleogene event that killed the dinosaurs, showed relatively rapid recovery. Diversity began increasing within a few 100,000 years. Ecosystems restructured within a few million years. But the Permian recovery dragged on for at least 5 million years, possibly 10 million or more depending on how you define recovery. Several factors likely contributed to the slow recovery. First, the environmental damage was simply more severe and longer lasting than in other mass extinctions. The Siberian traps didn't erupt once and stop. Volcanism continued, pulsing on and off for millions of years. While the main extinction-causing pulses occurred in the first few 100,000 years, continued gas release kept conditions hostile long afterward. Temperature, acidification, anoxia all persisted at levels that prevented ecosystem recovery. Second, the extinction itself may have disrupted processes needed for recovery. With productivity severely reduced, less organic carbon was being buried in sediments. This meant less carbon was being removed from the ocean atmosphere system. Normally, organic carbon burial acts as a negative feedback, gradually drawing down atmospheric CO2 and allowing the climate to cool. But with the biological pump broken, this feedback was weakened. Carbon accumulated in the ocean and atmosphere, maintaining warm conditions and preventing pH recovery. Similarly, with reef-building organisms extinct, carbonate sedimentation rates plummeted. Normally, the formation and burial of carbonate rocks removes carbon from the system on million-year timescales. This is another negative feedback stabilizing climate. But without coral reefs, without abundant shelled organisms, carbonate accumulation slowed dramatically. Again, a negative feedback was disrupted, allowing carbon to remain in the active system longer than normal. Third, the extinction may have created unstable positive feedbacks that maintained bad conditions. For example, if vegetation on land remained sparse, soil erosion would continue to be high. This would maintain high nutrient flux to the oceans, perpetuating algal blooms and anoxia. Anoxia would favour phosphorus release from sediments, providing more nutrients, creating more blooms, causing more anoxia. The system could be stuck in a loop, unable to break out without external forcing. Fourth, evolution takes time. The species that survived were generalists, tolerant of harsh conditions but often not particularly efficient or well adapted to specific roles. Rebuilding complex food webs, re-establishing specialized ecological relationships, developing new reef-building organisms with robust calcification physiology, all these required evolutionary innovation. And evolution works on timescales of hundreds of thousands to millions of years, especially when starting from low, diversity. Recovery finally began in earnest about 5 million years after the extinction, during the Middle Triassic. New reef builders appeared, not corals but hexactinellid sponges and unusual bivalves. Diversity began climbing. Community structure became more complex, but even then, the recovery was incomplete. Brachiopods never regained their Paleozoic dominance. They remain relatively minor components of modern marine ecosystems. Bivalves and gastropods, mollusks that had been less important in Paleozoic seas, inherited much of the seafloor. The ecological restructuring was permanent. When coral reefs finally returned in the Middle to Late Triassic, they were built by different corals. The scleractinian corals, the group that builds modern coral reefs, first appeared in the Middle Triassic. They may have evolved from soft-bodied ancestors, sea anemones that developed the ability to secrete calcium carbonate skeletons. They weren't direct descendants of the extinct rugose and tabulate corals. They represented an independent origin of reef building. Evolution had to reinvent the reef. The Permian-Triassic boundary marks a fundamental transition in the history of life. It's not just that many species went extinct. The entire structure of ecosystems changed. Before the extinction, seafloor communities were dominated by immobile filter feeders, brachiopods, crinoids, bryozoans, organisms that sat in one place and strained food from the water. After the recovery, mobile organisms became much more important. Gastropods that crawl across the seafloor grazing, bivalves that burrow into sediment, crustaceans that scurry through reef rubble. The shift from Paleozoic fauna to modern fauna wasn't just taxonomic replacement, it was a restructuring of how marine ecosystems function. There are uncomfortable parallels to the present day. Modern oceans are absorbing carbon dioxide from fossil fuel burning. The rate of pH change, while currently slower than the Permian event, is still faster than at almost any other time in the last 60 million years. Modern ocean pH has dropped from 8.2 to 8.1, an apparently small change that represents a 26% increase in hydrogen ion concentration. Coral reefs worldwide are showing signs of stress. Calcification rates are declining. Organisms that build calcium carbonate shells are struggling. Modern oceans are also losing oxygen. Measurements show dissolved oxygen concentrations declining in many regions, particularly in the tropics and at intermediate depths, exactly the zones that went anoxic first during the Permian extinction. Oxygen minimum zones are expanding. Dead zones are proliferating along coastlines, driven by agricultural nutrient runoff. The combination of warming, acidification, and oxygen depletion, the same triple threat that devastated Permian oceans, is beginning to manifest in modern seas. The comparison has important limits. The modern situation is different in crucial ways. The amount of carbon being released is much smaller, at least so far, than the Siberian traps released. The rate of emission, while high, is not as extreme. The oceans today start from a cold, well-oxygenated baseline, whereas Permian oceans were already warm and poorly oxygenated before the volcanic eruptions began. Modern ocean circulation remains robust. Thermohaline circulation shows no sign of shutting down, though some climate models predict weakening under future warming scenarios. Marine ecosystems today have much higher diversity than in the Permian. This potentially provides greater resilience, more evolutionary options, more species that might adapt to changing conditions. And humans, unlike the blind forces of volcanism, have the capacity to recognize danger and potentially mitigate it. We can choose to reduce emissions, to change our energy systems, to protect ecosystems. The geologically deterministic destruction of the Permian doesn't have to be our fate. But the Permian extinction teaches important lessons about vulnerability and thresholds. It demonstrates that warming alone, while harmful, might be survivable for many organisms. Acidification alone might be manageable. Oxygen depletion alone could perhaps be tolerated. But when all three occur simultaneously, when they combine and reinforce each other, the result can be catastrophic. The stressors interact, each making the effects of others worse. There's also evidence of threshold behaviour in the Permian event. Conditions apparently worsened gradually during the first pulse, then crossed some critical point during the second pulse, where damage accelerated dramatically. The system tipped from stress to collapsing. Understanding where those thresholds lie, what boundaries must not be crossed, becomes critically important when we're unintentionally pushing Earth systems towards similar conditions. The rock record from the Permian-Triassic boundary isn't just a story about the past, a curiosity for paleontologists to study. It's a natural experiment in global environmental change, preserved in stone for us to examine and learn from. The layers document not just what died, but how it died, not just the timing, but the mechanisms, not just the catastrophe, but the agonizingly slow recovery. Every fossil, every chemical signature, every sedimentary feature is a data point in understanding how Earth systems respond to massive rapid change. Some aspects remain mysterious and contentious. Scientists continue to debate details. Was the acidification truly global, or were some ocean basins buffered? How widespread was Ioneer at its maximum extent? What triggered the second pulse of carbon release when the first pulse hadn't yet finished? Why did some lineages survive when closely related ones went extinct? Different research groups favour different explanations. New data continues to refine our understanding, sometimes confirming hypotheses, sometimes overturning them. But the core narrative is solid, built on decades of work by hundreds of scientists studying rocks on every continent. The Siberian traps erupted. Massive amounts of greenhouse gases were released, temperature soared, the ocean acidified, circulation slowed or stopped, anoxia spread, euxenia developed. Most life in the sea died. Recovery took millions of years. This happened. The evidence is overwhelming, consistent across multiple independent lines of investigation. The question that lingers is not whether such catastrophes can happen. The rocks prove they can. The question is whether we're pushing towards something similar, whether human activity might trigger comparable damage, whether there are warning signs we should be heeding. The rates are different, the magnitudes are different, but the fundamental processes remain the same. Physics and chemistry don't change. Oceans still acidify when they absorb too much carbon dioxide. They still lose oxygen when they warm. Life still suffers when conditions change faster than adaptation can occur. The Permian extinction isn't a perfect analogue to modern change, but it reveals vulnerabilities in Earth's life support systems, weak points in the planet's regulatory mechanisms. It shows that stability we take for granted can break down, that thresholds exist beyond which damage becomes severe and lasting, that recovery from major disruptions is neither quick nor guaranteed, that ecosystems once destroyed may not return to their previous state even after millions of years. In the silence of those ancient limestone beds, in the dissolution marks etched into those final shells, in the geochemical signatures of toxic waters recorded in stone, we find a testimony. The oceans died once. They were murdered by their own chemistry, transformed from cradle of life into planetary poison. Life persisted, diminished and traumatized, clinging to existence in marginal refuges. Eventually, after eons, ecosystems rebuilt themselves, though into forms unlike what came before. The rocks whisper their warning across 250 million years. What happened before can happen again, if we're not careful, if we ignore the lessons written in stone. The scientific understanding of the Permian extinction has evolved remarkably over the past few decades. When the extinction was first recognized in the 1800s, scientists could see that something catastrophic had occurred. The fossil record showed an abrupt change in the types of organisms preserved. Below a certain rock layer you found trilobites, rugose corals, certain types of brachiopods. Above that layer, they vanished. New forms appeared, strange creatures unlike anything that came before. But the mechanisms remained mysterious. What could kill so many species so quickly? Early hypotheses focused on simple environmental changes. Perhaps sea level fell, draining shallow seas where most marine life lived. Perhaps temperature changed, dramatically. Perhaps there was a shortage of food. These ideas, while not entirely wrong, missed the complexity of what actually happened. They also couldn't explain the global nature of the extinction. How could a local sea level change in one region affect organisms worldwide? The pieces didn't fit. The breakthrough came with the recognition of the Siberian traps and their timing. Geologists had known about the enormous volcanic province since the 19th century. The basalt flows covering vast areas of Siberia were obvious even from early mapping efforts. But dating them precisely took technological developments that wouldn't arrive until the late 20th century. Uranium-led dating of zircons, refined through the 1990s and 2000s, finally allowed scientists to pin down when the eruptions occurred. And when those dates came back matching the extinction boundary within the error bars, the connection became undeniable. But proving the eruptions happened at the right time was only the beginning. Scientists still had to work out how volcanism in Siberia could kill marine life in oceans thousands of kilometers away. This required understanding the gases released, their effects on climate and ocean chemistry, the cascade of environmental changes they triggered. Each piece of the puzzle came from different types of evidence, different research teams, different methods. Boron isotope studies for pH, uranium isotope studies for anoxia extent, iron speciation for redox conditions, biomarkers for euxemia, carbon isotopes for emission rates. Each line of evidence independently pointed toward the same conclusion, building a case that became overwhelming in its consistency. What makes the Permian extinction particularly interesting from a scientific standpoint is that it wasn't a single catastrophe, but a sequence of linked events. The volcanism released carbon dioxide. The carbon dioxide warmed the climate and acidified the ocean. The warming disrupted circulation and created anoxia. The anoxia led to euxemia. The combination of acidification, warming, anoxia, and toxicity killed most life. Each step followed logically from the previous one, a cascade of consequences stemming from that initial volcanic trigger. Understanding this cascade helps us understand Earth systems in general, how different components interact, how changes propagate through the system. It also highlights the importance of rate. The total amount of carbon released by the Siberian traps, while enormous, wasn't unprecedented in Earth history. Other events, like the formation of coal deposits during the Carboniferous or the weathering of huge mountain ranges, have moved comparable amounts of carbon. What made the Permian unique was the speed. 36,000 gigatons released in less than 1 million years is fast. So fast that natural carbon sinks couldn't keep pace. So fast that life couldn't adapt. If the same amount of carbon had been released over 10 million years instead of 1 million, the ocean could have buffered it. Life could have adjusted. The extinction might not have occurred. This observation has direct relevance to modern concerns about anthropogenic climate change. Current human emissions are actually faster than Permian trap emissions per year, though we've been doing it for only about 200 years rather than hundreds of thousands. If we continue at current rates for another few centuries, we could release amounts of carbon comparable to what the Siberian traps released, but even more quickly. The Earth system has some capacity to absorb perturbations, but that capacity has limits. Push too hard, too fast, and you exceed those limits. The Permian extinction shows what lies on the other side of those limits. Modern coral reefs provide a particularly clear example of these vulnerabilities. Corals are extremely sensitive to both temperature and acidification. They live in a narrow environmental window, requiring specific temperature ranges, specific pH levels, specific carbonate saturation states. When conditions move outside that window, corals bleach, expelling their symbiotic algae, losing their colour and their primary food source. If stress persists, they die. We're seeing this happen in real time on reefs worldwide. The Great Barrier Reef has experienced multiple mass bleaching events in recent years. Caribbean reefs have lost over 80% of their coral cover since the 1970s. These are early warning signs. stress signals from ecosystems being pushed toward thresholds. Oyster farmers on the Pacific coast of North America have documented another troubling sign. In recent years, they've experienced massive die-offs of oyster larvae, the tiny free-swimming stage before oysters settle and grow shells. The problem traced to acidification of coastal waters during seasonal upwelling events. Deep water, naturally high in carbon dioxide from respiration and decay, rises to the surface during upwelling. In the past, this water was still supersaturated with respect to aragonite, the form of calcium carbonate oysters use. But absorption of anthropogenic carbon dioxide has pushed these waters toward undersaturation. Oyster larvae can't form their shells properly. Survival rates crash. The oyster farmers have had to adjust their practices, monitoring ocean chemistry carefully, moving larvae to better water when conditions deteriorate. These are not hypothetical future problems. They're happening now, visible consequences of changing ocean chemistry. They're not yet the mass extinction level effects of the Permian, not even close. But their movements in that direction, hints of vulnerabilities being exposed. If we continue on current trajectories, those hints could become larger problems. The question is where the threshold lies between manageable stress and catastrophic collapse. Scientists use the Permian extinction as a test case for Earth system models, the complex computer simulations used to project future climate change. If a model can successfully reproduce the Permian extinction, matching the observed patterns of temperature change, acidification, anoxia, and extinction selectivity, that increases confidence in its projections for the future. If a model fails to reproduce the Permian, that suggests it's missing important processes or feedbacks. Several research groups have conducted these Permian simulation experiments, and the results are instructive. The models can reproduce the broad patterns of temperature rise and carbon cycle disruption. They can generate ocean acidification and widespread anoxia. They can create euxinic conditions in regions where the rock record documents them. But reproducing the exact timing and magnitude of events remains challenging. Some models generate too much acidification, others not enough. Some develop anoxia too slowly or too quickly. The discrepancies highlight remaining uncertainties in our understanding of feedbacks and processes. But the very fact that models can approximate what happened, using known physics and chemistry, demonstrates that we understand the basic mechanisms. What the models struggle with most is predicting thresholds and tipping points. They can show that as carbon dioxide increases, temperature rises, ocean pH falls, oxygen declines. These are gradual, continuous changes, but at some point the system tips. Thermohaline circulation shuts down. Anoxia expands explosively. Ecosystems collapse. These nonlinear transitions are difficult to predict because they depend on factors that are hard to model precisely. Exactly when does circulation stop? Exactly when do feedback loops become strong enough to cause runaway effects? The answers depend on details of ocean stratification, ice dynamics, biological responses, carbon cycling feedbacks, all interacting in complex ways. This uncertainty works both ways. It means conditions might not deteriorate as rapidly as worst-case scenarios suggest. Natural negative feedbacks might kick in, buffering changes, buying time. But it also means conditions could deteriorate faster than expected if thresholds are crossed. Systems that appear relatively stable can shift abruptly once tipping points are reached. The Permian event shows both patterns. Conditions apparently deteriorated gradually during the first extinction pulse, then crossed some threshold, triggering the much more severe second pulse. Understanding where modern systems might have similar thresholds is a critical area of current research. One area of particular concern is the Amazon rainforest. Some climate models suggest that with sufficient warming and drying, large parts of the Amazon could transition from rainforest to savanna. The forest generates much of its own rainfall through evapotranspiration. Trees pull water from soil, release it through their leaves, creating moisture that forms clouds and rain. But if a large area deforests either through human cutting or through climate-driven die-off, rainfall could decrease. Lower rainfall would stress remaining trees, causing more die-off, creating a feedback loop. The forest could flip to a savanna state even if external climate conditions later return to normal. Once crossed, the threshold might be irreversible on human timescales. This is similar to what happened to terrestrial vegetation during the Permian extinction. The collapse of glossopterid forests wasn't directly caused by lava flows. It was caused by climate stress, warming and drying, that exceeded what the forest could tolerate. Once the forest died, soil erosion intensified, nutrient cycles disrupted, recovery became extremely difficult. The coal gap lasted millions of years because the forest couldn't simply regrow. The ecosystems had to rebuild from scratch, and that took geological amounts of time. Another modern concern is Arctic permafrost. Permafrost soils contain enormous amounts of frozen organic matter, the accumulated debris of tundra vegetation over thousands of years. As the Arctic warms, permafrost thaws. The organic matter decomposes, releasing carbon dioxide and methane. This adds more greenhouse gases to the atmosphere, causing more warming, causing more thawing, creating a positive feedback. Some estimates suggest permafrost contains more than 1,000 gigatons of carbon, potentially double what's currently in the atmosphere. If a significant fraction of that carbon gets released over the next century or two, it would massively amplify anthropogenic warming. This type of positive feedback may have operated during the Permian as well. Some researchers have proposed that warming triggered release of methane from marine sediments, specifically from methane hydrates, ice-like compounds that form under high pressure and low temperature on continental slopes. The initial warming from Siberian traps gases could have destabilized these hydrates, releasing methane, which is a powerful greenhouse gas, causing additional warming, which released more methane. Whether this actually happened during the Permian remains debated. The evidence is ambiguous, but the mechanism is plausible, and something similar could potentially operate in the future if ocean warming reaches critical thresholds. The deep time perspective provided by the Permian extinction also reveals something important about recovery trajectories. After a major extinction, recovery doesn't simply mean diversity returns to pre-extinction levels. The taxonomic composition changes. New groups rise to dominance, old groups remain suppressed. Evolution explores new possibilities. The recovery isn't a return to the previous state, it's the construction of something new. After the Permian extinction, brachiopods never regained their dominance. Before the extinction, brachiopods vastly outnumbered bivalves in most marine environments. After the recovery, bivalves dominated while brachiopods remained minor. This wasn't because bivalves were intrinsically superior. For hundreds of millions of years, both groups coexisted successfully. But the extinction hit brachiopods much harder. They lost more diversity, their ecological networks were more disrupted, they had fewer surviving lineages to seed the recovery. Bivalves, which came through the extinction in slightly better shape, exploited the empty ecological space. Similarly, the old-style Paleozoic reefs never returned. The rugose and tabulate corals went extinct, but more than that, the entire ecological structure of Paleozoic reefs disappeared. Reefs built by diverse communities of corals, calcareous sponges, bryozoans, crinoids, complex intergrown frameworks. When reefs finally returned in the Middle Triassic, they looked different. Different organisms, different structures, different ecological relationships. Evolution had reinvented the reef using new components. This has implications for thinking about modern extinctions and ecosystem degradation. Even if we stabilize climate, even if we stop habitat destruction, even if we prevent the extinctions we're currently driving, recovery won't simply restore what we've lost. The species going extinct now are gone forever. The ecosystems being destroyed are being transformed. If we eventually allow forests to regrow, they won't be identical to the forests that were cleared. If fish populations recover, the communities won't be exactly the same. Evolution will move forward, not backward. The question isn't whether we can preserve a static version of nature, but whether we can avoid damage so severe that recovery takes millions of years. The Permian teaches that recovery is possible. Life persists, evolution continues, new forms emerge, but it also teaches that recovery is slow, measured in geological time rather than human time. The 5 to 10 million years it took for marine ecosystems to fully recover from the Permian extinction is an incomprehensible timescale for human minds. All of human civilization, from the first agriculture to the present, covers only about 12,000 years. All of human evolution from ape-like ancestors to modern humans took perhaps 6 million years. The Permian recovery took longer. If we create damage on that scale, we won't be around to see the recovery. Neither will our descendants for thousands of generations. The Earth would eventually heal. Life would diversify again. New ecosystems would develop. But human civilization would be long gone. perhaps replaced by whatever intelligence evolves millions of years hence. This is the stakes we're dealing with, not the end of all life. Life is remarkably resilient, but potentially the end of a world recognizable and hospitable to humans. None of this is to suggest we're facing an imminent Permian-scale catastrophe. Current changes, while serious, are not yet approaching Permian magnitudes. The comparison is instructive not because conditions are identical, but because processes are comparable. The physics of greenhouse warming is the same. The chemistry of ocean acidification is the same. The biology of stress and extinction is the same. If we want to avoid the worst outcomes, we need to understand these processes, recognize warning signs, act before thresholds are crossed. The Permian extinction ultimately wasn't about the Siberian traps alone. It was about vulnerabilities in the Earth system that the eruptions exposed. The hothouse climate of the late Permian, the sluggish ocean circulation, the high baseline temperatures all made the system more fragile. When the volcanic stress hit, the system couldn't absorb it. The modern Earth starts from a different baseline, cooler and currently well oxygenated. But we're changing that baseline, warming the climate, altering circulation, stressing ecosystems. Each change makes the system a little more fragile, a little less able to absorb future perturbations. The ultimate lesson from the Permian isn't that volcanic eruptions cause extinctions. It's that Earth systems have limits. They can buffer changes up to a point, but beyond that point, they break down. Understanding where those limits lie, how close we are to them, what happens if we cross them, these are among the most important scientific questions we face. The Permian gives us a natural experiment to study, a glimpse of what lies beyond the boundaries of stability. It's a warning written in stone, preserved across 250 million years, available for those willing to read it. The oceans died once. They recovered, but it took eons, and much was lost that never returned. We have the knowledge to prevent similar catastrophes in our time. The question is whether we have the wisdom to use that knowledge and the will to act on it before it's too late.